I think most everybody was here last Thursday, but if you think about what we talked about, we were talking about hypothesis tests, where you're saying, okay, somebody's telling me something about a population. They're saying 20% of the students at Peaster believe in the Easter Bunny. So they're starting with a claim. And we're going to say, I don't think that many do. So we're going to come up with an alternate claim. Or I might say, I think more than that do. And then the hypothesis test says, all right, the first claim is called the null hypothesis. That's the original claim. And then the second claim is called the alternative. That's what you're really trying to prove. So now we're getting specific. Thursday was just in general. Now we're talking about how do you do this for a population proportion? We got 3 conditions for this test. We've seen them before. Sample has to be random. The NP times 1 minus P greater than 10. What's that saying? The sample has to be normal enough. And the individuals in the sample have to be independent from one another. Well, we can assume that if our sample size is no more than 5% of the population size. Okay, those are our 3 conditions that we've been talking about since when? Chapter 7? Way back. We're going to look at 3 approaches. First one's called the classical approach. Then we've got the p-value approach. And we're going to talk about each of these. And then the third one is the confidence interval approach. And you might be going, well, what's hypothesis testing got to do with confidence intervals? I thought we were done with those. No, not yet. All right, so let's just look at a silly example. Homer says that he can make 78% of his free throws on a consistent basis. You don't think it's that high. You think he's not telling the truth. So you go out to the basketball court, he gets warmed up, and he makes 16 out of 20, which is 80%. And he goes, that shows you I can consistently make 78% of my free throws. Does that prove that he can? No. This was just one day out there at the court. If you're in a sport where you keep track of averages like batting averages or free throw averages or whatever, it's based on a season, not just 1 or 2 games. So that doesn't necessarily mean that he can make 78% over and over and over again. Maybe he was just having a good day. When I played baseball, I could occasionally get a hit. Not consistently. All right, so another day you go out there and he makes 15 out of 20, which is what? 75%. And you go, okay, Homer, that shows that your claim about 78% is wrong. But does it show that? Not really. And why not? Because to really answer the question, either one of those questions, we've got to say, well, what's the probability of getting those results? Okay, Homer, let's assume that your 78% is right. How likely are you to make 75% of your free throws? Now see, this one, the 75% one, that's our side in this. We think it should be less than 78. So we're saying if your true percentage overall is 78%, how likely are you to make 75% on this sample, if you will, sample of 20 throws? Now, if you think about it, both the 80% and the 75% are pretty close to his claim. Neither one of them make us go, oh yeah, that's way off. No, they're both pretty close. So we don't have any reason to doubt his claim. We don't have proof to doubt his claim. We might still doubt it, but we don't have statistical evidence for it. All right, so here's what we do in a hypothesis test. Again, we're talking about proportions here. We start with the original claim, the null hypothesis, dead center in a normal distribution. All this depends on what? A normal distribution. That's why one of our conditions is that NP times 1 minus P greater than or equal to 10. That's the test for, is this normal enough? All right, so then there's our original claim, dead center. Then what do? We say, in effect, anywhere in this gray area, and notice it doesn't go all the way out to the tails, but we're just going to decide on a gray area there, and any place in there, if our sample hits, then we're not going to reject his claim, because anywhere in that gray area is not too far away from his claim for us to go, oh yeah, I'm going to reject it. This is the logic of it. Now you're going to decide where that gray area is before you ever do the test, before you ever do the sample. More about that in just a minute. So again, if it hits anywhere in that gray, we're going to say, don't reject the null. How close is close enough? We'll talk about that in just a minute. Here's something really important. Put a star by this. Just because we don't reject the null doesn't mean the null is true. Real important. In these hypothesis tests, write that down. You never say, therefore the null is true. No. No. We just don't have enough evidence to reject it. Think about a criminal trial. That's a hypothesis test. What's the null hypothesis? What do we walk into that trial with? Ma'am? No, not in our system of justice. Let's say Peyton is on trial. She's on trial for something. What does the prosecution have to do? Put on enough evidence. The null hypothesis is she's innocent until proven guilty. That's the null. We have to, if I'm the prosecutor, I have to bring enough evidence in that the jury goes, oh yeah, we can't believe that null anymore. She's guilty of sin. What if I'm the prosecutor and I don't give the jury enough evidence? We go back to the null. We can't reject it. It's the same idea in this. Now, does that mean she's innocent? No, she could have done it. We just don't have enough evidence to prove it. And that's what we're doing in these hypothesis tests. So if we hit in the gray area, we can't reject the null. That doesn't mean the null is true. Now, on the other hand, if we hit in what I colored red here, if we hit out there, now we are going to reject the null. How come? Because it's so far away from the null's claim that we're going, no. If that null really were true, why aren't we ending up out here in the boonies? The other day in class we talked about, all right, there's this girl, her boyfriend says he loves her. If he is out in the parking lot helping another girl change a flat on her truck, is that inconsistent with him loving girl number one? No. He's just a nice guy helping somebody out. If he talks to another girl in the hall, is that enough evidence to go, no, he really doesn't care about girl number one? Nope. Now, if she sees him walking in the cafeteria holding hands with another girl and kissing her as they walk in, okay, now we just crossed the line. That's all we're talking about here. There is a line that we can cross, and I colored it red right there. If we get out there, look what she's saying. She's saying, in the middle here, if you really do love me, if we just take that as true, then why am I seeing this action? It's not consistent with your claim being true. That's all a hypothesis test is. All right, so I'm just calling it the red zone. If we land out there, then the statistics term for being out there is that our results are statistically significant. You'll see that term used a lot in statistics. It just means we're pretty far away from that claim. In everyday language, it's this. If the null really is true, then why am I getting sample results like this? Yeah.
So when we're like deciding what the red zone is, like on a problem, is it going to tell us what the red zone is?
That is a great question. Yes, it is. Yes, it is. Great question. Don't know if you heard it, but she said, well, how are we going to know where the red zone is? Because we haven't been very specific about that so far. We just know if we hit out there, we're going to reject the null. If some plant says, we're only producing 3 millionths of, parts per million of this bad chemical into the water, and you do samples and it turns out to be 10 times that amount, then bells ought to be going off. No, their claim is not right. Something's wrong. And they actually use statistics when they're prosecuting companies for polluting and stuff. So, what's our first question here? How do you know where the red zone starts? Now we start getting into the different approaches. In the classical approach, we're just going by z-scores. If the z-score of the sample is far enough away, and we haven't determined exactly what that is yet, then we're going to reject the null. All based on z-scores. So let's go back to your claim, the alternative claim. You're saying Homer overall does not make 78% of his free throws. So here's what I did. I got a z-score. Notice what I did. This z ought to have a little 0 subscript under there. So I'm putting Homer's sample percentage here, the 0.75. Notice in red I'm putting the null hypothesis. That's in your formula pages, but I'm putting it in red to remind you that this number out here, the 0.78, is the null hypothesis. That's his claim. So that's going. What am I assuming? I'm assuming his claim is right until I can prove otherwise. So I got a z-score of negative 0.32. Now, what does that mean? One sec. That means the z-score for the sample is only 1/3 of a standard deviation away from the middle. Is that far away or close? Close. Yes, sir.
Is 20 the in, so like the total amount of cells in?
Uh-huh. That's our sample size. Good question. That's our sample size, the 20.
Is that formula?
That's your z-score formula. That started back when, chapter 3 or something? I think it goes that far back. So that means what? The results are not statistically significant, meaning we're not far enough away from the null to reject it. No bells going off, no red flags. It's just like, We could expect results like that. So we don't reject the null. Stop right there. Anybody have a question so far? We're just using logic and probability to figure this out. All right, so same question. The p-value approach. Now look at the logic here. We're saying if the probability of landing out there is pretty small, then we're going to reject the null. We haven't said what pretty small is yet. And we haven't said what's enough standard deviations to be out there. But we're just getting the idea here. So again, let's go back to the Homer problem. Again, I get the same z-score. So notice these two approaches have a lot in common. But now what am I going to do with that z-score? I want to find the probabilities. So if you'll get your formula pages out. Now we're going to convert that z-score to a probability. So I look in the table. What's the area that z-score represents to the left of it? What's the area to the left of that z-score? Exactly. Now, on the classical approach, I just worried about the z-score. In this one, I'm converting the z-score to a probability using the table. In other words, almost 37.5% of the area lies to the left of that z-score. What does that mean? That means we could hit out there in that tail, if you will, 37.5% of the time, assuming his claim is true. That's not rare at all. That's nearly 40% of the time we could expect to land out there just by chance, just by the randomness of the sample. Is that enough evidence to reject the null? Nope. It's not statistically significant. In the classical approach, we're just comparing z-scores. In the p-value approach, we're saying, okay, what's that z-score translate to in probability? Now notice those two approaches gave us the same result. Don't reject the null. Which one's more detailed? The p-value. The p-value is. And that's why most people use it now. Okay, let's keep going. So here's a list of different p-values and what they mean. Now remember, p-value is a probability. So if the probability of being out away from the null is 10% or bigger, we're going to say, you know, we don't have hardly any evidence at all. Don't reject the null. And then as the p-value, the probability again, gets smaller and smaller and smaller, the evidence starts building up. When the p-value gets less than 1 in 1,000 down here at the bottom, that's real strong evidence. Because why? The probability of getting the results that we did is so small that we can't believe that the null was true to begin with. That's just logic. If the null's true, why aren't we getting results that only can happen 1 in 1,000 times? Is this a miracle of some sort? Was this just the randomness of the sample? Well, probably not. Which brings us to, okay, whether we're talking about classical or p-value approach, how do you know where to draw the line? Good question. Before the test even starts, whoever's doing the testing decides on a level of significance, and it's called alpha. Well, we've seen alpha before. So you decide whether the level of significance is going to be 0.05, which is a common one, or 0.01, which is a common one, or 0.001, which is a common one. Notice what those p-values were, too, in that little chart right before this. think about when we did confidence intervals. We saw things like Z alpha divided by 2 and T alpha divided by 2. Well, that alpha is the alpha I'm talking about here. It's some level of significance. And so you're going to find out that confidence intervals and hypothesis tests are really closely related. So when you see alpha in these tests, and I can't think of a problem you're going to have that somebody doesn't tell you what alpha is. They'll say, use 0.05 for alpha, or use 0.01 for alpha. Because you have to know that, because that's where you draw the line. And once again, confidence intervals and hypothesis tests are really, really related. All right, here's the classical approach. In your textbook, that's in your notes, you can have a two-tail test, or you can have left tail or right tail. In the two-tail test version, if you hit out here in this colored area, either high or low, you're going to reject the null. Why? Because you're so far away from it. If the null's true, why are you ending up in the tails out there? And notice where the cutoff points are. Negative Z alpha divided by 2 and positive Z alpha divided by 2. And think about how that relates to confidence intervals. For a left tail test, notice it's just negative Z alpha or positive Z alpha for the right tail test. But if you end up in that colored area, you're going to reject the null. Otherwise, you don't have enough evidence. So for two-tail tests, look where the red zone starts. Of course, it's colored blue in that diagram. And for one-tail test, we're just talking about the single tail. Thank you very much. So in that colored area, that means we're far enough away from the null hypothesis to reject it. If it's true, why am I getting results like this? And here's a little reminder, again in the textbook. Just saying the same thing I did. Let's look at the p-value approach. Look at this. Same z-scores. But now we're talking about area. We want to know how likely are we to hit out there in that colored area. Let me say it even a better way. If the null is true, if we're going to say, yeah, I'll give you the null is true, then why am I getting results like this? And if we're out there that far away, I'm going to go, yeah, you're claiming the null, but I don't believe you. And the area equals probability in our table. Don't forget. Now here's the deal. If the p-value is smaller than alpha, you're going to reject the null. That wasn't true with the classical approach. We're just saying if the z-score for the sample is further away than that critical value, reject the null. Just remember, p-value, we're talking about area. We're talking about the probability of landing that far away. Here's the steps we're going to follow. Actually, I should have put B before A. Don't know what I was thinking. So, first of all, we're going to determine the null and alternative hypotheses. That's where we start. Then we check to see if our sample met the conditions. So we got what, 6 steps? All right, so based on a study that they did 2 years ago, 38% of adults with kids under 18 said that the family ate dinner together every night. Okay, that was then. Now, in a recent poll, they asked 1,122 adults, again with children under 18, do you eat dinner together 7 nights a week? And out of the 1,122 adults, 403 said, yeah. So the question is, has the percentage of families eating together 7 nights a week, has it decreased? That's the alternative hypothesis. That's what we're trying to show. So our null hypothesis is this, that P equals 38%. Now remember, P stands for the population proportion. P stands for the population proportion. But which population? The one 2 years ago or the one that we just did? Good, the one we just did, because that's the one we're asking about. We know about the other one. So in other words, this one I want you to write it out in words. That 0.38 represents our new families. The proportion hadn't changed. It's the same as the old. So it's the status quo, nothing changed. But it's talking about our new present day families. Okay, so what's our alternative? Well, the way the question's worded, is it less than 38%? And so in words, that means if we have enough evidence, then we could show that it has decreased. There's our hypotheses. Notice the null always has an equals. The alternative can have less than, greater than, or not equal to. Here it's less than. All right, so there's our hypotheses. Next we look at the conditions. First one was our sample random. And since this was a national poll, we can just assume they did it right. Okay, there's one hoop. Next one, is our sample large enough for a normal distribution? And we do that. NP times 1 minus. And notice the P I'm using there is the null hypothesis P. Because why? We're saying, assuming the null is true. And 264 is a lot bigger than 10. So yeah, we're talking about pretty much a normal distribution here. Third one, were the people in our sample, were they independent of each other? That's where the 5% rule comes in. Yeah, 1,122 is way less than 5% of families, say in the United States. So we meet all three conditions. That means we can assume we have a valid test here. Remember, we're making a guess. That doesn't mean we necessarily do, but we're assuming that we do have a valid test. So now I get the z-score for the statistic. See if you get the same thing I do. It'll help you to actually physically do this. So I have to find p hat. I came rounded off with 0.359. I get the z-score, and notice I did put the little subscript there, here. And once again, I'm using 0.38 in 3 different places because that's the null hypothesis. The only place p hat came in was that 0.359. Now, y'all, if it's 0.359, isn't that less than 38%? That's 35.9% for my sample. Doesn't that prove that the percentage has gone down? Nope. It did for this one sample, but is that result far enough away from the null to go, oh, no, we got really strange results here? No, we don't know yet. So let's see, what do I get for z-score? I'm getting negative 1.45. Remember, that's standard deviations. Now, what did the problem say alpha was? 0.05? So now we need to find out where's the cutoff point. So in your formula pages, look for an area of 0.05. Not a z-score, but an area of 0.05. What's the z-score that corresponds to? It's dead center between 2 values. Yeah, thank you. This. We have seen that number before. It was a critical value for what confidence interval? Yeah, thank you, 90. If I've got a 90% confidence interval, how much area is in each tail? 5%, 0.05, which is what alpha is here. So I'm hoping this starts coming together for you. This critical value is the same as what it would have been for a 90% confidence interval, because 5% is in each tail, and this is a one-tail test. Stop right there. Does that make sense? It might not yet, but tomorrow we're going to be working some more examples. So then what's our next step? We got to make a decision. Do we reject the null or not? And the classical approach is just based entirely on z-scores. So the z sub 0 is not less than negative z alpha. This is a left tail test. I made a little drawing here, as I'm prone to do, and look what it's showing you. It wouldn't hurt if you did the same thing. Here's our results from our sample with its corresponding z-score. Here's our line in the sand, our negative z alpha. Which one's further away from the middle? The negative z alpha. Our results didn't get far enough away so that we could reject the null. So our z sub 0 there is in that gray area that we shaded earlier. It's close enough that we can't reject the null, because why? It didn't make it to this cutoff line right here. That's the classical approach. Just go by the z-scores. If my result from the sample had been negative 1.72, then we'd say, oh yeah, reject the null because it's further to the left than our cutoff z alpha. Okay. So what's our conclusion? We know we're not going to reject the null. Here's a good way to write it. One sentence. So I'm mentioning alpha in there. And I'm saying at that level of significance, we don't have enough evidence to reject the null. And then write what the null is. It almost takes longer to write the conclusion than it does to do the problem. So in the end, we didn't have enough evidence at that level of significance, 0.05, to reject the null. So we can't say, yeah, it's decreased. We didn't have enough evidence to say that. But again, they gave us what alpha is. You're not going to have to come up with that. That's the classical approach. Let's do the same kind of thing with the p-value approach. Now notice something. The hypotheses, the conditions, and the z-score is the same for the p-value approach. We've already done those. Because remember, we're basing the p-value, which is a probability, on that z-score. So now what do we do? Remember, p-value is a probability. And we're saying, what's the probability the results from our sample, that z sub 0, is less than or equal to negative 1.45? And again, I made a little drawing. So our z-score puts us right there. We're finding the probability of hitting out here to the left of that point. So that area right over there to the left, and that left tail. Well, what is it in your formula pages? I got 0.0735. Is that what y'all are seeing? What does that mean? That means if the null is true, just for the sake of argument, say the null is true, how likely are we to get results out as far as we did or further? Well, 7% of the time. Is that less than alpha? Nope, alpha was 0.05. To reject the null, this probability that's 0.0735 has to be less than 0.05. It has to happen less than 5% of the time. We could get results like this 7% of the time. Which is more detailed, the classical approach or the p-value approach? P-value, yeah, I agree. Because looking at that 0.0735, man, I'm getting pretty close to 0.05. With the z-scores, you're just saying it either is less than that or it isn't. This gives you a number, a probability. So that's why most people are using p-values now. But remember, it's a probability. So we're wanting to hit in that area right there to reject the null. We didn't. So because the p-value is not less than 0.05, which was alpha, we don't reject the null. Now notice we got the same results. The classical approach said what? The z-score isn't far enough away. Don't reject the null. The p-value approach said, no, the results you got are greater than alpha, so don't reject the null. So our conclusion would be exactly the same. You don't have to copy it over again. It'd be exactly the same thing. So that's two approaches to a hypothesis test for proportions. Think about the logic of it. We're going to stop there. Tomorrow we're just going to work a couple of problems together. So this is 10.2. What do you think 10.3 is going to be about? Except this is proportions. What do you think? Means. And you'll already understand most of it because of what we talked about today. All right. Thank y'all.